Hello everyone. In this video, we are going to talk about random sampling, which is one of the most fundamental concepts in statistics. So, in computational statistics, random sampling plays a very important role. First and foremost, it allows us to make inferences about the entire population just from a sample. And this is incredibly powerful because that way, instead of surveying millions of people, we can just survey a few hundred or 1,000 people and still draw meaningful conclusions about everyone. That saves time, energy, and resources. When done properly, random sampling ensures our sample is representative of the population. In other words, the sample looks like a miniature version of the whole population containing all the important variations and characteristics. This method also forms the foundation of statistical theory. Many tests and methods assume the data to be from a random sample. If not, then the results might not be valid. Another key benefit of this method is that it allows us to quantify the uncertainty in our estimates. When we calculate statistics from a random sample, we can also determine how precise our estimates are likely to be. This gives us confidence intervals and margins of error that help us understand how to trust our findings. Finally, random sampling is also supports the validity of hypothesis testing. These are statistical procedures we use to make decisions about population based on sample data. Without proper sampling, these tests might lead us to incorrect conclusions. So now that we understand why random sampling is important, let's look at the different types of sampling methods we will deal with. The most basic type of sampling method is a simple random sampling, or SRS in short. This is exactly what it sounds like. Each unit has an equal probability of being selected. It's like pulling names out of a hat, as I mentioned earlier. Next, we have stratified random sampling. In this approach, we divide the population into non-overlapping groups or strata. Then we draw samples from each group separately. For example, if you're studying the students in a university, we might stratify by year, like freshmen, sophomores, etc., and then take random samples from each year. Then there's cluster sampling. Similar to stratified sampling, we divide the population into groups, but here we call them clusters. The key difference is that instead of sampling from each cluster, we randomly select entire clusters. For instance, if you're studying households in a city, we might randomly select certain neighborhoods or clusters and then include all the households in those neighborhoods. Finally, there is systematic sampling. Here we select units at a regular interval after a random start. So imagine lining up your population in a row, then randomly picking a starting point, and then selecting every 10th unit or 5th unit or whatever from that point forward. Each of these methods have advantages and disadvantages, and the best choice depends on your specific research question and the nature of your population. So we will begin with SRS. This is the most basic form of random sampling. In SRS, every element in the population has an equal probability of being selected. If your population has 1,000 people, then each person has exactly 1 upon 1,000 chance of being included in the sample. An important feature is that selection of one element does not affect the selection of another, which means that the events are independent. So if I select person A from my sample, that does not change the probability of selecting person B. Let me and in R, the implementation is very straightforward. So we use the sample function, we plug in the population, we select the size of our sample, and then we specify whether we want to implement replacement or not. So what this does is that it takes a random sample of 100 elements from our population without replacement, which means that once we have selected an element, we don't put it back in the pool for possible selection again. Simple random sample, or this method, is particularly useful when the population is relatively homogeneous, meaning that the members don't vary a lot on the key characteristics I'm studying. If the population has distinct subgroups with very different properties, we might want to consider other sampling methods to ensure that all these groups are properly represented in the sample. And that brings us to the next one, which is stratified random sampling. So this method is particularly useful when the population has distinct subgroups. In this approach, we first divide up our population into non-overlapping groups. We call these groups to be strata. These strata are based on characteristics that are important for the study. For example, if we are studying voting preferences, we might want to stratify by age, geography, income, and any other dimension that you might be interested in. After dividing the population into these non-overlapping strata, we take a simple random sample from each of these groups. This ensures that we get representation from each group in our final sample. In R, this is the template code to implement stratified random sample. This code groups our data into the data by the stratification variable, and then takes 0.1, which is 10% random sample from each group. Stratified sampling is extremely useful when the population has distinct subgroups and we want to make sure that each group is adequately represented in our sample. So if we are studying a rare disease, we might want to stratify by disease status to ensure that you get enough patients with conditions in your sample. One of the key benefits of this method is that it ensures representation from all important subgroups, and this can lead to more precise estimates compared to simple random sample, especially if the strata are homogeneous internally but different from each other. So let's walk through a practical example of how these sampling methods might be applied in a real-world research scenario. So suppose your research question is, do tech stocks have higher volatility than utility stocks? This is a perfect example of when stratified sampling can be useful. So our population in this case would be all stocks in the SP 500 index. To investigate this question, we might use a stratified method because we have two distinct subgroups we want to compare, tech stocks and utility stocks. So our sampling approach would involve identifying all the tech stocks in the SP 500, identify all utility stocks in the SP 500, then randomly selecting 30 tech stocks and 30 utility stocks. After selecting our samples, we would measure the daily returns for each of these stocks over a 1-year period. Then we will calculate the volatility, which is typically measured as standard deviation of the returns for each stock. And then we might do some other stuff. Now, the reason why a stratified approach works better is because if we just do a simple random sample of all the tech stock, of all from the entire population of SP 500, then there is no guarantee that the sample would have an adequate representation from tech and utility stocks. We might have a scenario where all the stocks that we end up selecting are from tech, or all the stocks we select are all from utility, or neither tech nor utility. So if we just do a simple random sampling method, there is no way of ensuring that the sample that we work with adequately represents the sample that we want. But by doing a stratified approach, we can ensure that both tech and utility stocks are not only there in the sample but are adequately represented. So this is the template code just for ease of convenience. There's a separate R script that I will discuss in a separate video. So um, to wrap up our discussion, let's just recap what we learned. So the first and foremost, random sampling provides the foundation for statistical inference. It's what allows us to make claims about populations based on sample data. Without proper random sampling, our ability to generalize findings would be severely limited. We have seen that the different sampling methods address different research needs. Simple random sampling works well for homogeneous populations, while stratified sampling works better when there are distinct subgroups. Cluster samplings can be more practical when dealing with geographically dispersed populations, and systematic sampling offers a straightforward approach for certain scenarios. Uh, we so this is the theoretical side. In a separate video, I will walk through an R script where I will show you how to implement these methods in R.